Hello, my name is Brian, and I will be taking you through the introduction and background information on our presentation about hybrid column store and row store database architectures. Here is a quick overview of what we'll cover today. We will start with the background information on row store, column store, and the hybrid store architectures. Then we will detail our experiment, including the setup and specific implementations. We use MySQL, MonetDB, and Highrise. Finally, we will dive into the results and analysis to compare the performance of each model and discuss potential future works in the area. To begin with, we have row store model. The fundamental idea here is that it stores the entire row or tuples in a continuous memory space. This structure is ideal for online transaction processing or OLTP workloads. OLTP involves frequent insertions, deletions, and updates of tuples, and often a mix of reads and writes on a few rows at a time. However, the row store architecture does have its limitations. It is slower for analytical queries that access few columns across many rows. In our experiment, we will be using MySQL for our row store benchmarks, but other examples include PostgreSQL and SQLite. Next, we have the column store model. This model stores columns continuously in memory. This is more optimized for OLTP or online analytical processing workloads. It's significantly faster with aggregate functions like max, min, sum, count, and average, and are often used in data warehouses. The efficiency comes from its ability to reduce I/O and memory usages because it only reads the necessary columns, such as when you need to find the average salary from an employees table. For our column store testing, we will be using MonetDB. Other examples includes Amazon Redshift and Google BigQuery. Finally, we will look at our hybrid store model. This architecture combines techniques from both column store and row store. This is ideal for mixed OLAP and OLTP workloads. The key benefit is its ability to adapt automatically to the best technique for the workload. It can partition a table vertically or horizontally. This involves determining which columns are frequently used or appear together in select statements frequently. There are, however, a few limitations. A hybrid store has a higher storage overhead due to the replicated data, and repartitioning is expensive, although automatic. Its performance is also harder to predict, and it's not optimized for purely row store or purely column store. We will be using Highrise as our hybrid store implementation.
Hello, my name is Cameron Solomway, and I will be covering the experiment section of our presentation. This section provides an overview of our methodology, dataset, and queries, followed by a deep dive into the performance of our three chosen database applications, MySQL, MonetDB, and Highrise. To ensure a fair and reliable comparison, we designed a specific experiment setup. First, we executed each query 25 times using the Python script. Then we discarded the first 5 runs as warm-up. This helps mitigate any caching or initial loading effects that could skew our results. The final performance of each query is the average execution time of the remaining 20 runs. You can see this on the right of the slide. For Q7, the average runs from run 6 to 25 is 50.792 milliseconds. For our tests, we used a dataset that simulates a typical enterprise employee database. The database includes 2 main tables, employees and salaries. Both tables are large with about 300,000 records. The data structure, as shown in the sample rows, is a standard relational data, allowing us to perform realistic OLTP and OLAP operations. We selected 2 sets of queries, OLTP and OLAP queries. OLTP queries are designed to mimic online transaction processing. They perform small, frequent operations, usually on a single row at a time. Our Q1 is a simple select that retrieves the full row where employee number equals 20,000. Our Q2 is an update to change the name of an employee at employee number 20,000. And Q3 is an insert where we insert a new employee and then remove that employee so we can run this query back to back to back. And then for our OLAP queries, or column heavy queries, these queries represent online analytical processing. They typically scan many rows but only a few columns, often involving some sort of sorting or aggregation function. Query 4 retrieves a few columns, first name, last name, and birth date, and then sorts that table. Query 5 and 6 perform a count, but then query 6 does a sort at the end. And then query 7 is our most complex one. It is a large-scale join across the two tables, employees and salaries, followed by an average and sorting. Our first system is MySQL. Since it's a traditional row store system, we expect it to perform well on our OLTP queries. A key feature of MySQL is its built-in persistence. It is able to save changes to the database, which is crucial for transactional integrity. During setup, we had some trouble importing CSV files on Mac OS, and we had to convert the data to a standard SQL file. For performance measurement, we use select now function before and after the query, which gives us a timestamp up to 6 decimals. For our row-heavy queries, query 1 executed in about 0.443 milliseconds, query 2 did it in 0.704 milliseconds, and Q3 did it in 0.638 milliseconds, which is very quickly. For our column-heavy queries, we can see they're much slower than the row-heavy queries. Our query 4 is about 120 milliseconds, query 5 is about 60 milliseconds, query 6 is about 55 milliseconds, and query 7 is almost 285 milliseconds. Next, we'll move on to MonetDB, which is a pure column system. MonetDB, we can expect performance of the inverse of what we saw in MySQL. So the row-heavy queries should be slower, and the column-heavy queries should be quicker. The benefits of MonetDB are that it is very fast for OLAP queries or analytical queries. Additionally, it supports very large data sets because it utilizes its disk space. Additionally, a limitation for MonetDB is that it is slower than in-memory systems like Highrise. In MonetDB, the results for the row-heavy queries were, as you'd expect, they were slower than MySQL. We had about 2 milliseconds for query 1, another 2 for query 2, and about 6 milliseconds for query 3. This shows an overall latency for OLTP queries. But for our column-heavy queries in MonetDB, we see they are much quicker than MySQL, with Q4 being about 7.5 milliseconds, Q5 being about 3 milliseconds, Q6 also being 3 milliseconds about, and then query 7 dropping down to about 6 milliseconds from that 285 we saw with MySQL. So this is a great improvement for the column-heavy ones. It's exactly what we would have expected. Finally, we look at Highrise. This is a hybrid stored database system. Highrise has no built-in persistence, so nothing is saved to disk. It lives entirely in memory. Additionally, we also had troubles importing CSV files with Highrise, so again, we used a MySQL or a .SQL file instead. The benefits are extremely fast computation since there's no data transfer from disk. Everything lives in memory, so it should be a lot faster. A limitation for this database application, though, is the limit of RAM is the limit of data you can store, since you don't use the disk for it. The goal of hybrid store systems are to adapt automatically to the best technique for the given workload. This should provide a balance of the positives of both MySQL and MonadDB. For our row heavy queries, we see the numbers are pretty fast, about 1.5 milliseconds for query 1, query 2 is about 3.5, and query 3 is about 1.2 milliseconds. And then for our column heavy queries, we see Q4 is pretty large at about 146 milliseconds, and query 5 has 13 milliseconds, query 6 almost 13 milliseconds, and query 7 down to 50 milliseconds. So overall, this is a little better, but it does have its limitations.
Hello, this is Bogon Kim, and I'll present our experiment results and analysis, and finally our ideas for future work. Here's the table that shows the average execution time for each query. To begin with the OLTP queries, MySQL, the row store system, consistently delivered the best performance. This outcome is expected because row store architectures can minimize the cost for modifying an entire tuple by storing full records contiguously in the memory. In contrast, MonadDB, the column store system, showed the highest latency, especially for inserts and updates. And HiRise, the hybrid system, showed competitive OLTP performance, better than MonadDB, although it is still behind MySQL. It shows that its hybrid design allows it to support transactional workloads reasonably well, even though it is not a pure row store system. Next, about the OLAP queries, MonadDB was the fastest, particularly in query 7, the join and aggregate query. It processed the query over 50 times faster than MySQL. This happens because column stores only read the columns required by the query, avoiding unnecessary I/O cost. HiRise showed an intermediate performance again. It performed much faster than MySQL for analytical tasks, showing that hybrid systems can capture many of the column store's benefits while still retaining reasonable OLTP performance. Overall, the result shows why HiRise aligns well with HTAB use cases, where both transactional and analytical workloads exist. Although HiRise already performs well in hybrid workloads, there are several areas where performance can be further improved. The first one is fine-tuning the chunk size per table. In the current HiRise implementation, chunk size is set globally across all tables. However, as shown in revised HiRise paper, the optimal chunk size can vary significantly depending on access patterns. For example, if the tables have OLTP-heavy workloads, they benefit from smaller chunks, while tables with OLAP-heavy workloads perform better with larger chunks. So a promising direction for future work is to implement a workload adaptive chunk size selection, which automatically selects the best chunk size for each table based on observed query behavior. And the second one is hybrid vertical and horizontal partitioning. According to the paper, the original design of HiRise was based on vertical partitioning, which means to split the table vertically and access each partition in a row-wise manner. However, the revised version introduced horizontal partitioning, which means to divide the table horizontally and access each partition in a column-wise manner. A potential improvement is to combine those two approaches, where a table is partitioned both by rows and columns. This could further reduce unnecessary I/O during query execution and better support workloads that contain OLTP and OLAP queries. Thank you for listening.